D of our worksheet notes where we introduce the new polar functions, limacons and lemniscates. So we're going to start by taking a rose, a single petaled rose that we looked at yesterday, and we're going to adjust the function and turn it into, first we're going to look at some limacons, and there are a couple different types of limacons, and we'll look at them all. But I'm going to take this function, and instead of just having it be this one trig term, what I'm going to do is I'm going to add a constant to that function, and we're going to see what happens. So if I make this instead of 2 cosine theta, 5 plus 2 cosine theta, then all of a sudden I have what, kind of still looks like it's a circle, but we no longer are going through that origin. But we're not centered on the origin either. And so this is what we would call a convex limacon. All right, it's nothing too exciting to look at, but we're going to look at all of the pieces of this limacon and all that stuff. But now if you were to look at the total distance across from point to point, that's now 10. All right, which you may look at this and say, well, that might be 2 times 5. That's not always going to be the case. But what you could do is from that origin, if you look out to the longer endpoint, we have a distance of 7. Whereas if you start at the origin and you move along the shorter distance, we have a distance of 3. And if you notice, the 7 and the 3, those are going to connect with that 5 plus 2 or 5 minus 2. So we do have a connection with length and these coefficients. All right, but that's one sort of limacon that you can have. That's a convex limacon. If I were to adjust this a little bit more, let's say I made this 3 plus 2 cosine theta. You see it's a little bit smaller now, but now we can say, well, this is definitely not circular, or it's definitely not a circle. It's got some circular aspects to it. But on the left-hand side, we've got this little divot. Got a little divot here. We call this a dimpled limacon. And that same idea of, okay, well, if I start at the origin and go the longer distance, I'm 3 plus 2 distance difference away, or 3 plus 2 units away, or 5 units. And then if I go the shorter one, I'm 3 minus 2 units away. We still have that same idea, but now instead of it having that nice curve, almost like a circle, we're going to dip back in to hit that point and then go out, sort of like we pushed in the edge of a circle. So this is what we would call a dimpled limacon. And there are 2 other types of limacon. So if I change this and I made it, say 2 plus 2 cosine theta. Now it's that dimple has been exaggerated so much, it's a nice sharp point. All right, so if we continue with that same idea of, okay, well, if I add 2 plus 2, that's going to give me my 4. That's going to get me from, the origin out that long distance for that petal. 2 minus 2 is 0. I shouldn't move anywhere, and that's what's happening here. So this is what we call a cardioid, because if I were to switch this a little bit, I made this say like negative, or 2 minus 2, and I switch that cosine to be a sine, you can see it's sort of a heart shape. And if I were to adjust these numbers a little bit more, say these are 4 and 4, and I were to zoom out a little bit, you can see it's even more of a heart shape. So we call these cardioids, or a cardioid limacon. Okay. There's one other one. And so if I adjust this just a little bit more, let's make this say a 2 here. As it's coming in, now think about if we were to subtract, 2 minus 4, I'd get negative 2. I have to come back inside, and it creates this loop on the inside. So we call this a looped limacon. All right, so there's limacons that we can have. There are 4 different types, and we're going to move over to our notes right now, and we're going to talk about those 4 different types and different characteristics that we can pull off of them to help us graph. equation that we're going to look at is called a lemniscate. And this is actually of the form r squared is equal to plus or minus a squared sine or cosine of 2 theta. So in order to graph it on the program, it has to be split into two different equations, a positive square root and a negative square root, so that it is actually a function that we're graphing. But what it does is it creates sort of either a two-petaled, you can think of this as kind of being a two-petaled rose, or sort of a bow tie-like shape. So if you think back to when we talked about roses, we said, you can't get a two-petaled rose, because if I did that, if I tried to do a two-petal rose, I would have to put in, like if I put in 2 in front of my theta, then I'm going to get 4 petals back. And so there were a certain number of petals that we can't get for our roses. This isn't actually a rose because it has a different format for the equation, but it does have just these 2 petals. And so sine is going to have these 2 petals either on, sort of, if you think about the positive 45-degree angle, or positive pi over 4 radian angle, or negative pi over 4 radian angle. I can go this way if I were to make this a negative inside my square root here. Or with cosine, I'm going to go either along the horizontal axis or the vertical axis. So these are another type of polar equation that we can have. We're going to go back to the notes in just a second, and we're going to look at the different forms and the different pieces of information that we can grab from them.